I think there's some pretty fascinating things about osmosis. First, let's look at the main things you should know. One is that you can get an actual buildup of pressure on the what we'll call the saltwater side. This could be, any solution. You could have sugar or whatever else dissolved in here. Uh, you'll get actually a higher level of that solution because of the osmotic pressure that that pushes through a semi-permeable membrane that separates the solutions. But it is the solvent that crosses the membrane. And yeah, the reason that osmosis can happen is that the solvent is small. If this is an aqueous solution, water is the solvent, and ions such as sodium plus, chloride minus, those are actually significantly bigger than water. And those ions, even though it's just one atom essentially, they're too big to go through the semi-permeable membrane. So you can kind of think of the semi-permeable membrane as like a filter with very, very small holes, like a very, very fine filter. And it filters like everything except the water. Yeah, we're just going to talk about water being the solvent. Now, which way does the water go through? It's going to dilute the more concentrated side. Another fancier way to say this is that the concentrations will become equilibrated. And yeah, so osmosis is not diffusion. In osmosis, the solvent moves. In diffusion, the solute moves to equilibrate the concentration everywhere. Well, technically, I guess osmosis is a diffusion of water, but not a diffusion of the salt or whatever is dissolved on the left side here. So now that you know the basics of osmosis, let's talk about osmosis in a real-world situation. Let's think about a red blood cell. Here it is. I'm putting this red blood cell in pure water, and the outside of the red blood cell functions as a semi-permeable membrane. So you can have osmosis occurring through the outside of the red blood cell. How's what's going to happen? Well, the water's going to move to equilibrate both sides. So the water is going to move to dilute the inside of the red blood cell. There are solutes in red blood cells. There's ions and stuff in there. And you're going to have that blood cell blow up like a balloon. You're going to have, as a result of osmotic pressure in that blood cell, hemolysis happening, where it basically just explodes like a balloon that got blown up too much. Now let's put that same red blood cell in, rather than a hypotonic environment where there's a low concentration of solute outside the cell, let's put it in a hypertonic environment where there's a high concentration outside the cell. So there's still some solute in the cell, but we're assuming there's significantly more solute outside the cell. Now water is still going to move to dilute the more concentrated side, so it's going to pass from inside the red blood cell to outside. So you're going to see water leaving the red blood cell to equilibrate the concentrations. And that's going to result in the red blood cell shrinking and shriveling up and again becoming useless. And this time the process is called crenation. There it is. So those are your key words here. Hemolysis in a hypotonic environment, crenation in a hypertonic environment. Here are your main concepts about osmosis that we just talked about. And if you understand this stuff, you're probably good to go on osmosis. Wait, one more thing. reverse osmosis. So if you want to get pure water, you can just apply a lot of pressure, maybe up here, pushing down on like a plunger thing, and if you apply a lot of pressure, you can push pure water into the pure water side and kind of collect that. But a fun fact about reverse osmosis systems, if you install one under your sink, they actually waste about 3 times more water than they create, because osmotic pressure is surprisingly strong. So if this saltwater side gets significantly concentrated, you're just not going to be able to apply enough pressure to keep moving water to the pure water side. So as soon as this stuff starts to get concentrated with ions and minerals and such, we have to get rid of it. Another fun fact about a reverse osmosis system is that you don't actually want there to be no ions in the water you drink, probably. It's helpful to get some, a little bit of sodium and such, maybe little magnesium, that kind of ion. So if you do get a reverse osmosis system in your house, you might opt for a remineralizer to put back some of the minerals that you took out through the osmosis. But yet another fun fact, there's about 3 pre-filters before you get to the really, really fine semi-permeable membrane that actually does the osmosis. So if you understand all that, you're good to go on osmosis. But I like to talk about why things happen. So you might ask the question, why is it that water just goes one way through the membrane? Can it just as well go the other way? And the answer is it does go both ways. It just goes more so this way than that way. If you think about these things on a molecular level, think about the molecules. They're just flying around, bouncing around, bouncing into each other, bouncing into the walls, bouncing into the membrane, and some waters bounce through the holes in the membrane. But on the saltwater side, the solute is just going to get in the way of the water. It might even block the path of the water to the little hole in the membrane. So the fact is that it's just more waters have more of an opportunity to go this way than the other way.